Group 14 elements, the carbon family. The carbon family, group 14 in the P block, contains carbon C, silicon Si, germanium Ge, tin Sn, and lead Pb. Each of these elements has only 2 electrons in its outermost p orbital. Each has the electron configuration ns2np2. Carbon is the 17th most abundant element by mass in the Earth's crust. It is available in nature in free as well as in the combined state. In elemental state, it is available as coal, graphite, and diamond. It is also considered the backbone of biology, as all life forms on Earth are carbon-based. In combined state, it is present as metal carbonates, hydrocarbons, and carbon dioxide gas, 0.03% in air. Carbon contains 3 isotopes, C12, C13, and C14. Carbon-14 is a radioactive isotope with half-life 5,770 years and used for radiocarbon dating. Silicon is the second, 27.7% by mass, most abundant element on the Earth's crust and is present in nature in the form of silica and silicates. Silicon is a very important component of ceramics, glass, and cement. Tin makes up 2 parts per million of the Earth's crust, making it the 49th most abundant element there. Tin occurs mainly as cassiterite SnO2. Germanium exists only in traces. Lead makes up 14 parts per million of the Earth's crust, making it the 36th most abundant element there. Lead occurs as galena PbS. Atomic, physical, and chemical properties. Electronic configuration. The valence shell electronic configuration of these elements is ns2np2. Covalent radius. As you move down in the carbon family, the atomic radius increases. We find that there is a large increase in covalent radius from carbon, silicon onward. From silicon to lead, radius increases gradually. This is due to the presence of completely filled d and f orbitals in heavier members. Ionization enthalpy. In general, the ionization enthalpy decreases down the group. Small increase in delta IH from Sn to Pb is the consequence of poor shielding effect of intervening d and f orbitals, an increase in size of the atom. Electronegativity. Electronegativity clearly decreases from carbon to silicon. But the electronegativity values for elements from silicon to lead are almost the same. Physical properties. All members of group 14 are solids. Carbon and silicon are nonmetals. Germanium is a metalloid. Tin and lead are soft metals with low melting points. Density. The density in carbon family increases as we go down the group. Melting and boiling points. Melting and boiling points show a downward trend as we move down the group, though a little haphazardly. Carbon and silicon form extraordinarily giant molecules and thus have large melting and boiling point. Chemical properties. Oxidation states and trends in chemical reactivity. Carbon family elements are tetravalent in nature since they have 4 electrons in their outermost shell. As the ionization energy of carbon family elements are very high, M4 plus hardly exists. On account of their low electronegativity, M4 minus also does not exist. Some of the compounds of carbon, like carbides, have carbon exhibiting a valency of C2 2-. Silicon does not form tetravalent or divalent cation. The other 3 elements, germanium, tin and lead, show both tetravalency and bivalency. Sn2 plus and Pb2 plus are more stable and common than Sn4 plus and Pb4 plus. In general, M4 plus compounds are covalent while M2 plus ions are ionic. As we move down the group, the ionic characteristics of these compounds increases. Elements other than carbon in this group can exhibit covalency more than 4. It is because of the presence of d orbital in them. Due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pairs from donor species. For example, the species like SiF6 2-, GeCl6 2-, SnOH6 2- exist. The hybridization of the central atom in these species is sp3d2. Reactivity towards oxygen. All members, when heated in oxygen, form mainly 2 types of oxides, that is, monooxide and dioxide of formula MO and MO2 respectively. Oxides in higher oxidation states of elements are generally more acidic than those in lower oxidation states. The dioxides CO2, SiO2 and GeO2 are acidic, whereas SnO2 and PbO2 are amphoteric in nature. Among monooxides, CO is neutral, GeO is distinctly acidic, whereas SnO and PbO are amphoteric. PbO solid plus 2HCl aqueous give PbCl2 solid plus H2O. XO solid plus 2OH minus aqueous give XO2 minus 2 aqueous plus H2O liquid. Reactivity towards water. Carbon, silicon and germanium do not react with water. Tin decomposes steam to form dioxide and dihydrogen gas. Sn plus 2H2O give SnO2 plus 2H2. Lead is also unaffected by water, maybe due to a protective oxide film on its surface. Reactivity towards halogen. Group 14 elements form halides with general formula MX4, CCl4, SiCl4, GeCl4, SnCl4, PbCl4, although some elements such as Ge, Sn, Pb can also form dihalides MX2. All other members except carbon react directly with halogen under suitable condition to make halides. Most of the MX4 X is equal to F, Cl, Br, I are covalent in nature. Exceptions are SnF4 and PbF4, which are ionic in nature. PbI4 does not exist. The tetrahalides of carbon, such as CCl4, cannot be hydrolyzed due to non-availability of vacant valence d orbitals, but other tetrahalides can be hydrolyzed. The central metal atom in these halides undergoes sp3 hybridization and the molecule is tetrahedral in shape. Heavier members Ge to Pb are able to make halides of formula MX2. Stability of dihalides increases down the group. At room temperature, SiF4 is a colorless gas, SiCl4 is a colorless liquid, SiBr4 is a colorless liquid, and SiI4 forms colorless crystals. SiF4 and SiCl4 can be completely hydrolyzed, but SiBr4 can be only partially hydrolyzed. Considering the thermal and chemical stability, GeX4 is more stable than GeX2, whereas PbX2 is more than PbX4. Hydrolysis of SiCl4. SiCl4 accepts the lone pair of electrons from water molecule in d orbitals of Si. This leads to the formation of SiOH4 as shown.